Thanks.
So we would like to invite the next speaker, is Paul Straus from Aerospace. It's invited talk.
The pointer at the screen in
Works
front of
very
you.
nice. Thank you. Okay, so let's see. So I'm going to talk about coverage and refresh, which is a big issue for radio occultation and how you want to express this, because radio occultation is I'll say, an odd sensor type. And what I mean by that is that coverage and refresh are typically the key metrics, or some of the key metrics, together with, let's say, accuracy and data latency, that you apply to a sensor that you might be flying for some observations. And typically, or many sensors in the past, they have some sort of a swath width. Maybe you have an imager of some sort, or some sort of scanning push broom instrument, perhaps conical scanner, perhaps. Basically, these sensors paint the surface of the Earth. So they fly over a region and they cover that region. And then when you say, well, how long does it take to refresh that data? Well, it's when they get back over the same area again. And they'll have an accuracy requirement. How accurately did I measure maybe a atmospheric profile or temperature profile or something like that in that region? So if you meet your accuracy requirement and you meet your coverage and your refresh requirement, you're very happy. The problem is that radio occultation, with its sort of pencil beam geometry, doesn't really adhere to that very well. You can think of it having some sort of a swath width, but there's only little pieces within the swath that we get. And when we say, well, what is the accuracy? Well, we can talk about the line of sight TEC accuracy along any individual occultation, but that's not necessarily what somebody that's an end user wants. They want the TEC accuracy, let's say, from some point on the ground to a point in space, maybe vertical, maybe not vertical. And so the issue is, now, how do you talk about coverage and refresh? Because you no longer have the ability to say, well, if I flew over this thing, now I have covered it. Not necessarily, because your ultimate accuracy is not the accuracy that the sensor provides. So in order to answer the question, you have to basically ask yourself, how many occultations do you need and where do you need them in order to achieve a certain accuracy of an end product, let's say the output of an assimilative model. And so I'm going to talk today about a way of doing this kind of analysis for ionospheric total electron content specification. A different application might be a different metric. I'm going to talk about the TEC application. Okay, so we have something, I'm going to call it Aussie-like. It's not entirely an Aussie, and I'll talk about where that's different. We start with an orbital simulation. We calculate the lines of sight for that simulation. We have a truth model. In this case, we're using WAM-IPE, and we generate TEC along those lines of sight. And then we do an ionospheric inversion, but we're not using an assimilative model as part of that. This is just a linear algebra inversion of the system. And then we evaluate the performance of that solution relative to the truth. We're going to look at just mesoscale features. We're not looking at really tiny things. We're going to avoid the auroral zone and low latitude turbulence, because those are highly structured. We're talking about the larger scale features in the ionosphere. We're going to start out to simplify this, and I'll just comment again, this is a work in progress, so this is sort of a status report, you may say. We're not looking at the entire globe, we're looking at a region of interest. I'll talk about that a little bit more in the next slide, but basically it's a 30-degree half-angle cone in latitude and longitude, and a 200 to 900 kilometer altitude region that covers the bulk of the F region peak. You can see the grid spacing that we're using there. 2 by 4 degrees, and then in altitude 47 kilometers, relatively coarse. I'll talk about that later. A key assumption is we're just going to assume temporal stationarity. So in other words, the ionosphere is frozen for a period of time. Right now, we'll say an hour. And we take all the measurements that we could make from a constellation and say, can we, during that time period, retrieve the truth with the ionospheric data that we've got from our simulated orbits. I'll say at the moment also one other simulation, one other simplification is for zenith TEC. And most studies, I think, just focus on the occultation TEC, but there's TEC above the spacecraft, and that can be quite important, especially if you're embedded in the ionosphere, you get some upward looking looks. But in this case, we are just measuring vertical TEC above us. We are not simulating that yet. We do plan that in the future. So we don't realistically model the zenith TEC. Let's see. Yeah, so we replaced the overhead arcs by this just a vertical TEC measurement in our analysis as a simplification initially. So why did we pick this particular region of interest? It comes from climatology. This is from IRI, a solar maximum situation. You can see, you know, the bulk ionosphere is maybe a little bit raised in altitude, whether relative to what it would be for solar minimum. And basically 90% of the TEC is coming from altitudes between roughly 200 kilometers and 900 kilometers. So that's where the altitude region comes from. We figure if you can do a good job retrieving that, then through extrapolation and minor corrections, even if you're an error on the bottom side, on the very bottom side and the top side, your accuracy of your TEC is still going to be pretty good. And we wanted to consider the size of the region enough to be able to incorporate basically two things. One, we're using our metric is total electron content from the ground, not necessarily vertical, could be slant path. So we want to have that incorporated in our analysis. You can see on the left picture talks about the geometry that requires. If you go down to 20-degree elevation angle, then you need about an Earth solid angle of a little less than 15 degrees. That corresponds to a certain region of the ionosphere you want covered. If you look at now with the occultation perspective on the right, it depends a little bit on the altitude of your satellite, but the Earth observation angle is now larger because the lines of sight are so long across the limb. You get it between, let's say 42 to 49, I'll just say 45. So ideally we wanted to do a plus or minus 60-degree solid angle for our cone in latitude and longitude. Now we ended up with 30 degrees. We had some runtime considerations. Those have since been resolved, but at the beginning of the problem, we had to make a compromise, and we started out with the 30, that's where the 30-degree cone came from. So when you're doing these kinds of analysis, you're free to pick whatever observation constellation you like. So we decided to go with overkill to start with. And some of these you'll recognize, or some will recognize from UCAR analysis, the altitudes and inclinations, same as what was mentioned in a NOAA study, but now we're talking many more satellites. So we have 3 shells of 1,024 satellites each. Each shell has a Walker constellation, 32 by 32, 32 planes, 32 satellites. We'll note on the mean anomaly shift to keep uniform spacing. And then the altitudes of the shells are, as you see there, and the inclinations, low inclination, moderate inclination, and a little bit higher inclination. We simulate all 4 GNSS constellations that provide lots of observations. And in terms of the RO sensor capability, we're looking for a cosmic 2-like field of views, which basically goes out to plus or minus 70 degrees in terms of the anti-velocity and the velocity direction. And we also consider maybe this receiver that we're flying can only measure GPS, or maybe it's very capable and can measure all 4 constellations. So this produces a very large number of rays, as you can imagine. Just for the GPS only case, for example, with a 5-second simulation time step, which by the way was determined to match so we don't skip over any voxels in the analysis, you almost have 2 million rays over the 1-hour time period. And again, that's 3,000 plus LEO satellites. But many of these rays are redundant. They don't provide that much additional information. And so we are winnowing out the rays to ones that we consider quote unquote unique. And there's 2 features that we look at. We look here at the lower left, you can see a sequence of rays, again, a 5-second time step between our simulation. And sometimes we're hitting a voxel, right? Well, that's just counted as one touch. We may have a sequence of 4 rays that all hit the same voxel, but we only consider that to be touching the voxel one time. It's passing through that. So 3 of those would not be unique out of if there were 4 that went through. More importantly, we sort of consider this from a tomographic perspective. And the idea was, well, if you're going to do a good job of retrieving, you want different look directions going through all the voxels. It's not enough to say, oh, I touched this voxel somewhere along my ray path. You have to have crossing views of that voxel, or you're never going to get a good retrieval of the ionosphere if there are significant gradients. And you can see, so this is an example for a particular voxel, and these little colored fans represent, you know, different occultations that are passing through the voxel, but some of these are not very unique. They're almost at the exact same angle, and this is now in a north-looking geometry, not azimuth relative to the velocity vector. So we basically, for each of these colored fans, we would throw out everything except for one pass, and that eliminates a whole lot of rays. Perhaps by about a factor of 100 relative to the starting point. And we have something of an ad hoc parameter. We picked 10 degrees as this azimuthal uniqueness parameter. There was a little bit of analysis behind that, but it's largely ad hoc. Okay, so what is it? What do we do then? We start with our overkill situation, 3,000 satellites, and we do our inversions, and we see how well they perform. And we vary the number of shells. We can throw away a third of the 2/3 of the constellation and just look at one shell. If we do that, we will pick the middle inclination and altitude. That's the shell that we're keeping. Or we can change the number of orbit planes or the number of satellites per plane. And for each one of these cases, we're adjusting the Walker F parameters to maintain a uniform distribution of satellites. I'll say that's semi-qualitative evaluation. We don't have a rigorous process, but we're trying to maintain which ones are we throwing out. We want to have a residual set which is fairly uniform. So each time when we do this inversion, again, this is a very large scale linear algebra problem. You either get a case, you have 3 cases. Either the inversion is full ranked, which is basically overdetermined. You've got more than enough data to solve the problem, and you end up with a perfect solution to the problem. You're able to completely retrieve the ionosphere. Or maybe it's what we call near field full rank. I'll say marginally underdetermined. Some of the voxels that you retrieve will have errors, but when you integrate through them, then the TEC is really not very much impacted because it's just a few voxels that have errors. So that's the intermediate case. And then, of course, if the inversion is underdetermined significantly, then we get large TEC errors. So now we've also, I'm not going to spend too much time on this, but we've included noise, sensor noise in the process to test the solution stability. And right now, the 2 cases where we get fairly good results, either good results or fairly good, they're not significantly impacted by noise. So this is the overall results at a very high level, a little complex, and I'm going to kind of brush through this quickly because my time is running short. You can see the 1 shell are the open figures, the 3 shells are the dark figures, and we are having them colored now by whether it's overdetermined, no errors, marginally determined, insignificant errors, or underdetermined, where you can't really use it. And you can see as you add more sensors, then things go from red to blue to black. And they're organized by whether or not you can have a receiver which is able to check all 4 satellites or all 4 constellations or 1. And when things become in blue and black, that's when you can make a statement and say, okay, I've got enough RO sensors out there to fully determine my ionosphere. And you can see, depending on which GNSS capable receiver you have, it's going to be in the 24 to 48 sensors or a couple of hundred sensors. So just switching topics just a little bit, what kind of accuracy are we talking about? Here we get perfect retrievals for our analysis because of the way we stated the problem. But in the real world, a key factor is whether or not the spatial scales, particularly horizontally, support the kind of measurements that we see. If we were trying to retrieve, for instance, bubble structures in the equatorial region, which have large density variations over small scales, we're not going to see that at 2 by 4 degrees. We're never going to get there. So that's where we're going to have errors. And similar, if you have gravity waves or some other structure which has a significant TEC impact, and it's over a smaller scale than your model can support, then you can't see it. So in order to evaluate that, we looked at some real data. So this is not occultation, it's ground-based data. You can see, there's various tracks. We sorted the tracks from the ground in terms of tracks that are mostly going north-south versus tracks that are mostly going east-west. And we look at the gradients along those tracks. This is a quiet day example, so it's sort of an easy starting point. And we can generate these curves of what the cumulative slant path TEC gradient distribution looks like. And we say, what's the 80th percentile, where we have most of the tracks, we have that mostly characterized. We did evaluations in 3 longitude sectors, and we come up with these kinds of results. And I won't go into too much detail here. You can see things coded here. I'll just mention one thing in the night side. We actually, the day that we picked to analyze, which was February 3rd, 2023, we happened to have bubbles in the night side on that day. So I'm actually not showing you that day for the red curves that go through the equatorial region. I'm showing a different day that didn't have bubbles. If I showed you the day that had bubbles, that curve goes off the chart because there's high structure there. That's the case we're trying to avoid. You're going to need a lot more data to be able to evolve those kind of spatial scales. And you can see the lists here. And again, I'm going to brush through this. But the key issue at the bottom here is that through some analysis, we can now say, okay, if I want to specify TEC on these grid scales, which is 2 by 4 degrees, right, the WAM-IP size, my accuracy can't be better than 1 to 5 TEC units. Yeah, I can't get there. So just a summary and future plans. Again, this is a sort of midpoint briefing, if you will. So some caveats. If the ionosphere could be characterized by the grid states that we have, which obviously that's not a perfect statement, but if it was, and if the study assumptions, the stationarity, the regional analysis, don't represent substantial differences relative to the real world, okay? So it's a ballpark number that we're looking. Then you need about 36 uniformly distributed RO sensors measuring all 4 GNSS constellations to provide an accurate TEC specification. And the level you can do it is 1 to 5 TEC units. Okay. So there's a variety of open issues. Obviously, we have some assumptions. We have this poor vertical resolution. We need to fix that. We're currently using an absolute TEC approach in our inversion algorithm. We need to go to relative because that will be better, more consistent with propagation of sensor noise. We got to get rid of the overhead ray paths that are non-physical and replace them with realistic paths. And then we need to expand the region of our solver a bit more. Maybe we don't have to go global. We want to go more global than we are. So we have plans to do all that kind of work, and we're in the middle of doing that. Any questions?
Thank you, Paul, for exciting talk. We have time for 1 or 2 short questions.
Sorry, so I missed the transition from thousands of satellites.
Well, we start out with happy overkill, but remember that we are, in other words, we start out that thousands of satellites. That's the black point in the upper right-hand corner. 3,000 satellites.
Oh, I see. That's it.
Okay.
I see it.
And we're
Okay.
winnowing down the planes and satellites per plane and cutting it down until we can't get a solution that is good, where things go red.
But you really wanted to bound the solution.
Yeah, we want an estimate to how much RO do you need. Now, I will comment that when you talk about a real world case you're using now an assimilative model, it's not going to be exactly like this. Still, as long as our stationarity assumption is not too bad, I think that's the main one, then you would expect that that kind of analysis would result in a similar sort of assessment. And again, this is now connected through the relationship between the horizontal scale size and TEC, the structure in TEC. You can get a connection between that and a minimum capability. And then finally, I'll just mention that if you reduce the size, I do expect at some point, right? I mean, RO is mostly on the limb, although you get the overhead that gives you some horizontal structure. At some point, the solution will not be stable as you reduce the grid size small enough, right? And then that's the limit of what you can do with RO. But I don't know where that point is. We still have to fix our model, get rid of some other errors, and maybe we'll be able to have a better answer at some point.
Yeah, well, I think in the ionosphere, the logic of what you're doing makes sense because the models really aren't filling in very well, at least In other words, the forecast isn't there, which means the model
Correct.
physics isn't filling in
Yeah,
gaps
it's
that
different
well.
than in the neutral atmosphere. Basically, the models that I'm aware of, which again, people are always developing, so maybe my knowledge is not 100% up to date, but the models typically have some sort of underlying either climatological model or a physics model, and then you add a Kalman filter assimilator on top of that, right? So what we don't have, although people have talked about ways to do it, is you don't have a way to take the physics of the ionosphere and make your specification better, right? Now, if you had that, right, then you're going to do better with fewer satellites because now you're able to use the physics and your understanding to do that. But I don't think that's been demonstrated yet. And I know folks are working towards that, but until you get there, this is where you are.
We have another question from John.
So Paul, super interesting. And, you know, what would happen if you would put like an in situ sensor on there that was measuring density or something? And so you would really have a shell or 3 shells where you could really specify density at a shell. Do you think that that would make you better?
I do not think so. I mean, obviously it provides additional data and you could provide other data types also. I mean, this is exclusively RO, but you can look at other things. My sense is that the in situ data would provide you with so-called an anchor point, but without a way, you need some physics to take that anchor point and extrapolate it elsewhere. So I think, like I said, this is I'll say, I don't know if it's a worst case, but it's a little bit of a pessimistic estimate saying, hey, we aren't smart enough yet to use the physics well in our models so that we need less measurements to do a good job. And I'll also say this applies to near real-time specification of the ionosphere as opposed to forecasting where you're going to worry about what's the solar wind coming to you, how does that couple, that gets much more complicated.
We have final question from Irfan.
So again, thanks. Very interesting work. Great to see that progress. Question that maybe it's my lack of understanding on this plot on the y-axis, you have a number of unique observations. So what's the period? What's the time period over which you have to make these unique
1 hour.
1 hour. Okay.
Yeah. And again, I'll just comment, you know, this is, you remember we started out with 1 million plus, or maybe 4 times that much or 3.5 times that much if you have 4 constellations. So you can see the factor, we have got down to 1.2 times 10 to the 4th out of that million. So we threw away piles of data in order to do this analysis because those weren't considered quote unquote unique. That term does, the air quotes are important in that case. There could be value in that data. As a matter of fact, some of our more recent studies are saying that there is some value and we were maybe a little bit, threw away a bit much.
Okay, thanks the speaker again.